When we talk about aging, the conversation,
Hmm.
it almost inevitably turns to decline. Specifically, we discuss the steady decline of our body's defenses.
Right, a process scientists call immunosenescence.
And we know this decline is why older adults are less able to fight off new infections, why vaccines aren't quite as effective for them, and, why they're generally at a higher risk for cancers.
It's a huge global health challenge, no question.
But that's the accepted reality, how we've always approached aging.
It is. But, and this is a huge but, recent large-scale population studies have completely upended that traditional view. They're showing us this massive contradiction.
Which is?
While protective immunity definitely wanes with age, the risk for developing many serious autoimmune diseases actually steadily increases the older you get.
Wait, that completely breaks the model.
Yeah.
If your immune system is collectively running out of steam, failing to launch aggressive responses against external threats like viruses or tumors, then why in the world is it suddenly gaining the ability to launch incredibly aggressive, tissue-destructive attacks against itself?
It's the ultimate paradox. Logically, we'd expect that as your overall immune competence goes down, the incidence of autoimmunity should fall too. You can't launch a self-attack if your troops are too tired to march.
Of course.
Yet we see incidence rates for conditions like rheumatoid arthritis, psoriasis, and crucially, giant cell arteritis, peaking sharply in later life. This forces us to re-examine the whole nature of immune aging.
And that leads directly to our deep dive today. We are exploring a fascinating and really counterintuitive hypothesis that the decline we usually worry about immune aging might actually be a necessary host protective adaptation.
Exactly.
And the core driver for late-life autoimmune disease isn't the decline, but the failure of that decline. We're looking at the mechanism where retaining what the sources call immune youthfulness in later life is the exact thing that drives aggressive diseases like the autoimmune vasculitis, giant cell arteritis, or GCA. Okay, let's unpack this.
It's a profound shift from viewing aging strictly as a collapse to viewing it potentially as a controlled slowdown.
Historically, doctors and researchers tended to see autoimmunity as a problem of the young, right? Often young women, because diseases like lupus tend to show up early.
It was stereotyped as this condition of a hypervigilant, overzealous young immune system that, hadn't learned its manners yet.
But that view just doesn't hold up.
Not at all. Not under population-wide analysis. The sources we have, including a massive study following 22 million individuals, they confirm that about 10% of the population gets diagnosed with an autoimmune disorder over their lifetime.
10%? Wow.
And here's the key finding. The highest likelihood of receiving that diagnosis occurs decisively in the second half of life.
That's a striking statistical pivot, especially for anyone trained under the older paradigm.
It is. And when you look at certain diseases, the age dependence is absolute. Polymyalgia rheumatica, or PMR, and our model disease today, GCA.
They're almost exclusively diagnosed in people over 50.
You just don't see them in younger adults. You don't. And this proves that there are age-dependent biological mechanisms that somehow manage to accelerate self-destruction, while at the same time, our ability to fight tumors and pathogens is failing. It's a real double-edged sort of aging.
So we have an immune system that's slowing down, yet it's becoming incredibly susceptible to self-attack. If we accept that self-tolerance was successfully imprinted in youth, the system knew what was us and what wasn't, then something must be changing in the aging body to challenge that.
Exactly.
What is the fundamental problem the older immune system is dealing with?
The problem is saturation. The sources describe it perfectly as an age-related flood of neoantigens.
A flood of neoantigens.
Essentially, as we age, we accumulate this massive, overwhelming antigenic load. The body is encountering millions of new targets that look like self, but are just different enough to trigger a response.
That sounds like a constant state of emergency. Can we break down where this flood is coming from?
We can group the sources into maybe 4 categories: chronic stimulation, genetic instability, waste management failure, and then chemical modification.
Okay, let's start with chronic stimulation. I'm guessing that relates to viruses we carry for life.
Exactly. Chronic infections are relentless. Viruses like the chronic herpes family, Epstein-Barr, or EBV, cytomegalovirus, CMV, they cause constant low-level antigen release.
Right.
They also induce subtle ongoing damage to host tissues. This endless background noise constantly stimulates the immune system, increasing the supply of self-antigens and keeping T cells on a slow burn.
It's like having a car alarm that keeps going off for small things, so when a real threat comes, the system is already kind of fatigued and confused.
Precisely. And that confusion is compounded by the second source, genetic and proteomic instability.
So mutations.
Yes, aging naturally brings increases in DNA and RNA mutations. These mutations sustain the formation of neoantigens, brand new proteins the body has never seen before.
Yeah.
Now, we rely on this process for cancer defense.
Which is good.
It's good, but it's inherently risky for autoimmunity
No.
because these novel targets can pop up in non-cancerous tissues too. It's a classic trade-off. Better cancer protection, but higher autoimmune risk.
I see the trade-off. Okay, so moving past the creation of new targets, but what about the physical environment? What's happening to the actual structure of our cells and tissues?
That brings us to our third source, dysfunctional proteostasis. It's a high-level way of saying failed waste management.
Failed waste management. So the cleanup crew is failing. What does that look like at the cellular level?
It just creates inflammatory debris. The sources note two key issues here. First, aging T cells start littering. That's the term they use. They release waste-filled exosomes that float around and create pro-inflammatory cells.
And the second issue.
Second, there is insufficient efferocytosis. That's the specific process where specialized cells safely clear away dead and dying cells.
So if efferocytosis is the cleanup crew, we're saying the older host's crew is on permanent strike, letting all this flammable waste build up.
That's the perfect analogy. You now have chronic inflammation fueled by genetic instability, viral stimulation, and uncollected cellular garbage. But here's where it gets really interesting.
Okay.
The final source, which deals with how that garbage becomes highly immunogenic, post-translational modifications, or PTMs.
Tell me more about PTMs. I know they're chemical changes, but how significant are they here?
They are massive. PTMs are chemical alterations that happen after a protein is made, and they're highly dependent on chemical stressors that build up with age. They fundamentally changed the shape and identity of the long-lived proteins in your body.
Can you give us a concrete example?
Sure. Decarbamylation. As we age, urea, a waste product, breaks down into isocyanic acid. This acid then chemically reacts with lysine residues on long-lived structural proteins, like the collagen holding you together.
And that reaction permanently changes the protein's structure. So the protein that was once cell now has this chemical tag on it, making it look foreign.
Exactly. And combined with things like oxidation and glycation, these processes lead to the accumulation of what are called advanced glycation end products, or AGEs.
And this is what causes tissue stiffening and the breakdown of those critical fibers. The protein fragments become a new type of antigenic debris.
Yes. And the vessel wall, which has been stretched and stressed for decades and is rich in these low-turnover matrix proteins, is particularly susceptible. It becomes this highly immunogenic reservoir. It's like a self-destruct mechanism built into our tissues.
Okay, so we have an environment that is just saturated with new, suspicious self-targets. Now we come back to the core paradox. Given this massive flood, what should the immune system's most adaptive response be?
Right. If initial self-tolerance is threatened, what's the best play?
You're suggesting that if the system can't trust its targets anymore, the best strategy is just to disengage.
It is the counterintuitive hypothesis.
Yeah.
Hit the brakes. The age-related decline of the innate and adaptive arms reducing T-cell activity, limiting their diversity, that might actually be a necessary host protective process.
To shield you from yourself.
Exactly. It shields older individuals from tissue-destructive autoreactivity by effectively slowing down their responses to that accumulating flood of neoantigens.
So the decline we see isn't just a failure, it's the body deliberately shifting into a kind of damage control. It's choosing a slow, safe response over a fast, but potentially mistaken one.
That's the key takeaway of this new model.
So what does this all mean for diseases like GCA? The problem isn't that the immune system declined too much, it's that this protective decline failed to happen. The patient is stuck with a system that is inappropriately responsive.
Suffering from sustained immune youth. Precisely.
And GCA is the perfect model for this.
It's perfect because it's a vasculitis inflammation of blood vessels that is strictly age-restricted, always over 50. And it specifically targets the major elastic arteries, the very tissues rich in those chemically modified proteins we just talked about.
So the disease is sustained by two age-inappropriate failures that should have stopped the response. Let's look at failure number one, the persistence of these so-called young cells.
Right. This involves stem-like memory CD4 plus T cells, or TSCM cells. Normally, these stem-like populations, which can rapidly renew and fuel long-term responses, they gradually decline as we age.
But not in GCA patients.
In GCA patients, this loss rate is slower. Their critical T-cell populations are functionally younger than their chronological age.
And these useful, tireless T cells are the source of the attack. Where do they live, and how do they stay young when the rest of the body is aging?
They reside in these specialized inflammatory structures that form near the inflamed artery, often called tertiary lymphoid structures, or TLSs. These are essentially autoimmune T stem cells
Why?
because they continuously self-renew and rapidly generate massive numbers of the pathogenic effector T cells, the actual aggressive cells that invade and destroy the vessel wall.
That sounds like a continuous, self-replenishing supply chain for destruction right there in the artery wall. What's giving them that fountain of youth?
It's a distinct survival niche. The key mechanism is an interaction between a receptor, NOTCH1, on the T cells, and its ligand, jagged1. And this ligand is aberrantly expressed by the endothelial cells lining the microvessels in the inflamed artery.
So the artery itself is sending a signal to the T cells saying, stay young, stay active, keep attacking. This NOTCH jagged interaction is basically a T cell rejuvenator.
It's an inappropriate maintenance signal in a very dangerous environment. That's failure 1.
Incredible. Okay, now let's look at failure number 2. Even if those stem cells are providing a continuous supply of T cells, those cells are constantly exposed to chronic antigens in the vessel wall. They should eventually tire out. We rely on T cell exhaustion to shut these things down, right?
We do. Exhaustion is a critical host protective mechanism. When a T cell is chronically stimulated, like in cancer or a chronic infection, it develops inhibitory receptors or checkpoints like PD-1. They act as an off switch.
A safety break.
Right.
But in GCA, the T cells are just relentlessly functional.
They are non-exhaustible, even against those chronic arterial wall neoantigens.
So where's the breakdown? Is it the T cells themselves or the cells trying to signal them to shut down?
The problem lies with the signal, specifically with the antigen-presenting cells, or APCs, the macrophages in the vessel wall. The sources point to chronic stress in these APCs, which shows up as endoplasmic reticulum, or ER stress.
And that stress is sabotaging the stop signal.
Precisely. The ER stress causes the APCs to trap their inhibitory ligands, the stop signs, specifically PD-L1 and CD155, inside the cell. They never make it to the cell surface to interact with the T cells off switches.
So the macrophages are essentially naked of their inhibitory signals. They can't apply the brakes.
That is the perfect way to visualize it. They break the PD-1, PD-L1 checkpoint. The result is that the continuous supply of autoreactive effector T cells
From failure 1.
generated by those persistent SMED cells is now entirely unopposed. That's failure 2. And that uninhibited aggression is the definition of GCA.
Wow. This paints such a detailed and tragic picture of the new disease paradigm. It's a perfect storm. Age-inappropriate immune youth combined with an age-related deficiency in the APCs, all happening in the face of this overwhelming neoantigen load.
And it's not just a theoretical model. We see this mechanism confirmed in real-world medicine. The source points out that this T-cell youthfulness is also what we see in tumor-infiltrating T cells.
Which is why they respond so well to checkpoint inhibitor therapy in cancer.
Exactly. In cancer therapy, we are deliberately trying to achieve that sustained immune youthfulness state by blocking the off switch. We're preventing protective exhaustion so the T cells can fight the tumor.
And what's one of the most common and feared side effects of that therapy?
Severe immune-mediated adverse events, often including a vasculitis that looks a lot like GCA.
It makes perfect sense. We are artificially creating the exact set of conditions, uninhibited young T cells in the presence of neoantigens that drive this late-life autoimmunity.
It confirms the central thesis. If primary tolerance fails to contain that lifetime flood of neoantigens, the age-related decline of the immune system truly is a necessary protective element. It's an evolutionary compromise.
That's a huge synthesis. When we look at the ultimate takeaway here, the current data suggests that achieving a functional and healthier immune system in older adults, what everyone calls immune rejuvenation, comes with a potential, maybe even an unavoidable cost.
Right. The calls for maintaining and improving immune competence in older adults are strong, and they're ethically necessary. But if sustained immune youthfulness can be this detrimental, we are forced to ask a really difficult question.
Which is?
Does restoring a functional immune system inevitably mean accepting a higher risk of pathogenic autoimmunity? That may be the price we have to pay for a younger immune system.
A fascinating and slightly unnerving thought to end on. Thank you for guiding us through this deep dive into aging, tolerance, and the unexpected risks of staying too young.